Um, so welcome everyone to our weekly seminar. Today I'm very happy to introduce Jingjing Shi. Jingjing and I met during our PhD in Trieste. After that, she held a postdoc position at the KIAA in Peking University, and then she moved to IPMU, where she is now. She's an expert in galaxy intrinsic alignment and galaxy halo connection. And today she will tell us about her work on galaxy intrinsic alignment. And so whenever you're ready, take it away.
Okay, thank you. Thank you, Alina. First, I want to thank you for having me remotely visiting WCA. And it's a pity that I can't go on site, but I hope today we can have some interesting discussions. So the goal of the pre-season cosmology is to understand the origin, the composition, and the evolution of the universe. CMB, cosmic microwave background, is one of the main probes that we have for constraining our cosmological models. From the features shown in CMB, we know now that our universe is made up of 27% of dark matter, 5% of ordinary matter, and 16.8% of dark energy. Those numbers are quite accurate. However, what we don't know is what is dark matter and what is the dark energy. The other open question is related with the early universe. So is inflation the right model to describe the early stage evolution of the universe? Is the primordial density fluctuation Gaussian? To answer those questions, we have to go beyond the CMB. So the density fluctuations we see on the CMB map will collapse due to a gravitational force, and they form virialized dark matter halos. And within dark matter halos, stars, galaxies can form, and they make up the large-scale structure that we see here in this map. So the late time, to trace this late time structure growth and expansion, we can use several probes. We can use galaxy clustering. We can also use type 1a supernova, galaxy clusters, or gravitational lensing. So for example, the light from the background galaxy will be distorted by the foreground gravitational potential well. This can cause an elongation of the galaxy image that we observe. And when the gravitational potential well is very strong, we can see those arcs, those features on the observed image. This is a strong lensing. Well, when the intervening gravitational well is not that strong, we don't see clearly distortion by eye, but we can still statistically extract such distortion signal from observation. This is known as the weak lensing. So with those probes, we can put constraint on the cosmological models, mainly characterized by the cosmological parameters shown here. However, tensions exist when we compare the constraint from early universe and that of the measurements from the local universe. For example, there is this 4.4 sigma tension on Hubble parameter between the measurement done by CMB and the measurement in local universe from strong lensing of type 1a supernova. This tension could either mean that there is some unknown systematics during the measurement, either in the early universe one or in the late universe one. However, it can also mean that there is some new physics. So for example, if we change the equation of state parameter W for dark energy, so make it non-zero, or if we allow the curvature of the universe to be not zero, we can somehow make up 2 to 4% of the early universe Hubble parameter measurement. And if we are considering, for example, dark matter interaction, early dark energy model, or we allow some additional relativistic particles, we can make up like 5 to 8% of the discrepancy on this Hubble parameter. There is another tension on S8, which is basically related with the amplitude of the density fluctuation. This tension is also between CMB and the big lensing measurement. It's not as severe as Hubble parameter, but it's still a 2.3 sigma 1. The ongoing and upcoming image and spectroscopic survey will help us to confirm the above tension, and it can improve our current constraint on cosmological parameters by reaching to large scale coverage, by reaching to fainter galaxies and higher redshift. Here I highlight HSC and PFS survey, which is run on the Subaru telescope, and I'm also a member of those 2 surveys. So under this context, a galaxy intrinsic element, which is the correlated shape, correlated intrinsic galaxy shape or orientations, can put a major challenge on the weak lensing cosmology. On the other hand, it can also be used as a probe of cosmology and galaxy formation physics. So these 2 aspects are the things that I'm going to focus in my talk. The tidal field is thought to be the main origin of a galaxy intrinsic element. For ellipticals, which are dispersion dominated, it's thought that the intrinsic element is mainly produced by the gravitational stretching. So during the collapse of the elliptical galaxies, the stretching force by the tidal field will make the galaxy ellipsoid and also align with the tidal field. Well, for these galaxies, people usually think angular momentum is the main factor that decides what we observe for the shape. The angular momentum is thought to be originated from the tidal talking, which is described in the cartoon here. So when the major axis of the proto-galaxy and the kind of like the major axis of the tidal field misalign with each other, there will be a tidal torque exerted on the proto-galaxy from the tidal field. So this torque will spin the galaxy up and produce the intrinsic element that we see. So for the gravitational stretching one, the intrinsic shear of the galaxy is found to be proportional to the tidal field. Well, for the tidal talking one, the intrinsic element, the intrinsic shear that for the galaxy that we observe is found to be proportional to the square of the tidal field. So comparing to the first one, the spin element is a weaker one. And the parameter the minus sign means that if C1 is larger than 0, the galaxy is aligned with the major axis of the tidal field. And this C1 depends on galaxy properties and such as luminosity, stellar mass, or morphology, and so on. Those are all incorporated in the C1 parameter. So for galaxies lie at a given redshift, because of the tidal field, because they share the same light scale structure, the intrinsic shape already correlate with each other. This is known as the II intrinsic alignment signal. Well, the light emitted from this galaxy will pass through the matter along the line of sight. So those matter, this line of sight matter will distort the observed galaxy images, causing this is the signal that we are interested in, called in cosmic shear cosmology. It's donated by Gigi here. And there is another intrinsic alignment signal. Well, it's originated because for the matter that distort the background galaxies, they are also like producing the intrinsic shape for the galaxies that lie in those light scale structure. So this will cause an extra GI intrinsic alignment signal. And well, because studies have shown that GI is like order of magnitude higher than II. So it's the main signal that contaminates the cosmic shear cosmology. So in this work, I focus mainly on the GI intrinsic alignment signal. So if intrinsic alignment signal is ignored, it can bias our cosmological parameter constraint. This is shown by this figure for elucid wavelength measurement, for example. The black contour is the fiducial cosmology, and the right dashed contour is the case when intrinsic alignment are totally ignored. So this means that we need to proper modeling or observation for the intrinsic alignment signal so we can mitigate its effect on the cosmic shear studies. So this can be done using the formalism that I mentioned previously. For elliptical galaxies, because the intrinsic shear is proportional to the tidal field according to this gravitational stretching formalism. So the intrinsic alignment signal of the GI signal is found to be proportional to the linear power spectrum. And mu here is the cosine of the angle between K and line of sight, and DZ is the growth factor, and C1 rho critical 0 is just a constant that has been calibrated by some intrinsic alignment observations. And this AIA parameter is the parameter that I'm going to talk a lot in the following. In the following. So this is a parameter that characterizes the strength of the intrinsic alignment signal. And this is the so-known the linear alignment model. So if we replace the linear power spectrum here by the non-linear one, we have the non-linear alignment model. For the case of tidal talking, because the intrinsic shear is proportional to the square of the tidal field, so it's rather weak one. And in the linear case, the spin intrinsic alignment is going to disappear when we go to large scales. So those two models are found to be match the observation rather well at large scales. For example, this is the measurement done in Sloan-Losey luminous red galaxies. for large scales, you can see that the linear alignment model works very well. If we go to slightly smaller scales, the nonlinear alignment model works well as well. For the blue galaxies, we don't see, for the blue galaxies, which people cannot like think, spin is the main factor that decide the shape that we observe. There is no clear intrinsic alignment signal detected so far. So this is kind of like in agreement with the quadratic alignment model at linear in the linear case. However, if we go to smaller scales, for example, here, none of those, the nonlinear alignment model doesn't work. This is because the small scales is complicated by the nonlinear and also bionic physics. So this is when we kind of like, we start to turn to cosmological hydrodynamic simulations because we kind of like believe those are the best we have so far for studying the hard to analytically model bionic and nonlinear physics. So in our work, we use illustrious TNG 300 to study the intrinsic alignment of galaxies at different scales, redshifts, stellar mass, morphologies, and environments. So illustrious TNG 300 is a simulation of box size 300 megaparsec, and it contains physics such as star formation, supernova feedback, magnetic field, agent and agent feedback, and so on. And the simulation is large, the box size is large enough for us to have a very good statistics in, and its resolution is also good enough for our purpose. So typically the shape, we can only observe the projected shape. So we can not observe the 3D shape of the galaxies. So in observation, the shape of the galaxy is typically characterized by the light distribution. In simulation, however, people either use the stellar distribution or the angular momentum. Well, because this like no matter what kind of galaxies they all have angular momentum and they all have the stellar distribution. So in our work, we did both. So for each galaxy in the simulation, we measure the shape. We characterize the shape by the ellipticity using both the stellar distribution and also angular momentum. And with the ellipticity, we can obtain the shear of the galaxies. Here, R is the responsivity parameter, which is just 1 minus the dispersion of the ellipticity. And we did the E mode and B mode decomposition to make our results more clear. So the B mode intrinsic alignment signal for the GI signal, so for the cross correlation between matter field and shear disappears because of the parity symmetry. There is B mode II signal, however, it's mainly originated from the nonlinearity. And we think E mode is the most important. So in our work, we focus on the E mode and we just use the B mode intrinsic alignment signal as a consistent check. We use newly developed statistics called intrinsic power spectrum for our purpose. So the intrinsic alignment power spectrum is basically defined here. We try to cross correlate the E mode shear with the correlate the galaxy E mode shear, and we also do the cross correlation between the E mode shear of the matter field and also field by the galaxies. So this intrinsic power spectrum is it's a 3D one. It's not a projected 2-point correlation one, which is commonly used in other works. And we think the good thing is it contains the full information on 2-point statistics, and also it gives a high signal to noise ratio measurement. So we first check the stellar mass and redshift dependence of the galaxies in Illustris TNG. So this figure here shows AIA as a function of the scale, which is basically the intrinsic alignment strength, how it depends on the scale. At small scales, we can see the intrinsic alignment signal gets stronger, which is reasonable because this is basically the one halo region, and it describes how, for example, if it's a central, it describes how the central galaxies align with its dark matter halo. Well, on the relatively large scales, this intrinsic, this AIA is become constant. So this is consistent with the prediction of the nonlinear alignment model. We also found the intrinsic alignment signal is stronger for massive galaxies. Well, probably you all know this already. And we don't find we didn't find we didn't find a strong redshift evolution, basically no redshift evolution. And because we measured intrinsic alignment by cross-correlate the E-mode shear with either the matter field or the galaxy field, we found there is a discrepancy at small scales for those two measurements, which is kind of like saying the nonlinear effects in the dense region weakens the intrinsic alignment of galaxies. However, at large scales, those two measurements agree with each other, which is a very good thing because this is saying that as a large scale intrinsic alignment signal is kind of like free of the small scale bionic physics and so on. So in the following, I will mainly talk about the shear cross-correlate with the matter field. So we further studied intrinsic alignment signal for centrals and satellites. We found a very strong signal for the massive centrals. And the circles here are for the shape, characterized ellipticity, while the squares here are for the spin characterized ellipticity. So in the, well, if in the ideal case, the spin is aligned with the minor axis of the ellipsoid. So we should expect those signals, they are the same. But actually there is a misalignment between the spin and the minor axis. So they are not always agree with each other. But we found for the central, massive centrals, those, the spin tend to be aligned very well with the minor axis. Well, for some low mass satellites, the signal is not so good. And we also found a non-zero spin alignment signal at that scales, which is kind of like inconsistent with prediction of the quadratic alignment model, because nonlinear, we think it's mainly because the nonlinear evolution of the matter density field at this scale. And for satellites, we found at small scales, their shape, there is a radial alignment, which is saying that the satellites tends to point towards the centrals. And at some large scales, we found the alignment signal is reversed, which is very interesting. However, this is also very different from measurements in other simulations, such as massive black. And we think this is a very specific prediction of Illustris TNG that probably that can be tested in the observation. So the intrinsic alignment signal is also depends on the morphology. we found the strongest signal exists for the massive spheroid. For disks, we don't see a clear, for massive disks, we see some intrinsic alignment signal for the shape, but we don't see clear signal for the spin. And for the low mass disks, the signal is even reversed. This is inconsistent with the known spin flip phenomenon, which is saying that for low mass galaxies, their spin tend to be aligned with the filament, while for massive galaxies, their spin is kind of like perpendicular to the filament. This is the first time that we have shown this phenomenon in a two-point correlation statistics. Well, in the end, we asked ourselves, like, can we measure this intrinsic alignment signal in the coming surveys? So we consider the case for the luminous red galaxies and emission line galaxy surveys. We did a very rough selection by ranking the stellar mass and star formation rate. However, I think in some semi-analytical model, they found that ranking the selection of ranking the star formation rate for emission line galaxies kind of like agree with the emission line strength selection. So it's just a rough, it's a not a very accurate selection, but should be okay. So we found for the luminous red galaxy so massive galaxies, there is, we can obtain a good intrinsic alignment signal even up to redshift 2. However, for those emission line galaxies, we don't see a clear intrinsic alignment signal. And we also estimate the possible signal to noise ratio for those two samples. So if our measurement can reach the scale of saying like K equals roughly 2, for the case of PFS-like and DAISY-like survey, we can obtain a signal to noise ratio of intrinsic alignment of 8. However, if we can increase the number density, we can significantly increase the signal to noise ratio results. So on the other hand, as I mentioned before, intrinsic alignment signal, it can be also used as a probe of the cosmology because it's originated from the tidal field. So it contains information of the light scale structure. And my previous like talk kind of like, I hope probably give you this hint that it also can be used to constrain the galaxy formation physics. So there is, so people have done some Fisher matrix analysis showing that, so if we include intrinsic alignment signal, if we combine intrinsic alignment measurement with a galaxy clustering measurement for a BOSS-like survey, we can obtain roughly 1.5 times a tighter constraint of the growth factor and also the Hubble parameter. This is true up to redshift. This is true up to redshift 1. However, the inclusion of intrinsic alignment signal gets like contribute less if we go to higher redshift. There is also work like done by previous students in Kavli IPMU showing that this intrinsic alignment signal can be a very special probe of anisotropic primordial non-Gaussianality. So this figure shows that for the isotropic primordial non-Gaussianality, the galaxy clustering or halo clustering is at large scales like it's a good probe. However, for the anisotropic primordial non-Gaussianality, it shows no difference from like the Gaussian one. Well, this is different if we use intrinsic alignment signal So it shows very different signal from the isotropy primordial Gaussianity and the Gaussian one. So in this situation, if we want to measure, we ask ourselves, so suppose we want to use intrinsic alignment signal to constrain cosmology. So what are the chances in the context of the upcoming survey? We have, for example, PF survey that will probe the cosmology using emission line galaxies up to redshift of 2.4. DAISY will target luminous stripe galaxies up to redshift 1. This is good. But for higher redshift, it's also emission line galaxies up to 1.6. However, as I shown previously, in observation, there is no, in both observation and simulation, we don't see clear intrinsic alignment signal for those emission line galaxies. But we know from simulation that the dark matter halos that host those emission line galaxies, they have clear intrinsic alignment signal. It seems that there is a way to extract the intrinsic alignment signal of emission line galaxies. It's just that we need a new shape estimator. As I mentioned before, typically in the observation, the shape of the galaxy is characterized by the light distribution, and it's applied by a certain weight, shown by the W here. And in simulation, people typically use the stellar particle distribution to measure the initial tensor. And one of the most commonly used is the so-called reduced initial tensor, where it's the particle distance relative to the center is weighted by 1 over r squared. So it's distance to the center. With this initial tensor, we can obtain the ellipticity of the galaxies. So in our work, we first need to select emission galaxies. This is done in a very similar way as I mentioned previously. So we simply rank the star formation, rank galaxies using their star formation rate until their number density reaches the typical number density for the emission line galaxy surveys. And this table summarizes the samples used for our work. You can see that they have a very high star formation rate, and the central fraction decreases once we go to the lower redshift. However, at redshift of 2, 18% of them are centrals. And the stellar mass is roughly stays constant, and the halo mass only increases slightly if we go to lower redshift. So to develop, so motivated by the idea that we need a new shape estimator, we want to do it as realistic as possible. So we for those emission line galaxies selected from the simulation, we did a ray tracing simulation. For example, this is image surrounding an emission line galaxy with moving with a size of 1 megaparsec multiplied 1 megaparsec, and also the depth of the line of sight is also 1 megaparsec. So during this ray tracing simulation, we also considering the attenuation due to diffuse interstellar medium and dust. And the first panel here, it's showing the I-band projected luminosity surrounding an emission line galaxy at redshift 1.5 without considering any observational effects. And the middle panel here shows that what we expect to see after we considering the sky background noise and also the scene effect in the image. We consider the case for the observation of the Subaru telescope. And the last figure, we only show the pixels with signal to noise ratio larger than 3. So we define a new aperture shape estimator based on those image simulations. For each emission line galaxy, we use the flux surrounding it within a radius of 500 kiloparsec in moving space. And we derive the initial tensor using this. So here is just a comparison of what people typically use in the simulation for the reduced initial tensor. So comparing with this one, our new ship estimator include large aperture, and it puts no 1/r² weighting for the fluxes. We also, based on those initial tensor, we calculate ellipticity. So this is our main result. We found that using our shape estimator, we can obtain an intrinsic alignment signal that basically agrees with what we expect to see if we use dark matter particles centered on these emission line galaxies. However, this alignment signal, this intrinsic alignment signal is not seen if we use the reduced initial tensor. This is originated from the correlation that we see between the ellipticity of using ellipticity calculated with dark matter and ellipticity calculated using our aperture initial tensor shown here. Although there is the scatter is not so small, but it's surprising that we can recover the intrinsic alignment signal of dark matter halos. And if we compare the ellipticity calculated using the reduced initial tensor with the dark matter, we don't see a good correlation. This kind of like explains the result shown here. So this result is somehow consistent with what people see in the observation. For example, this is intrinsic alignment measurement done in low Z sample. So the Gaussian annihilation one is the one that gives more weight into the center region of the galaxy, while the one cooler one and isophoto one is the one that gives more weight to the outer region. And the isophoto one is found to show the strongest intrinsic alignment signal that we observe. This and the author saying that the idea by this result is that the outer region of the luminous red galaxies are more responsive to tidal field. However, our work, we extend to larger regions than the galaxy. We include the dark matter, we extend to the dark matter field. So this is a brief summary. This is a summary of this talk. I found I finished really quick, but probably it's okay. So we did the 3D intrinsic alignment power spectrum in the cosmological simulation. With this, we have the full 2-point correlation information. We also have the full information on the intrinsic alignment signal scale dependence. And we also studied the stellar mass, redshift, scale morphology, and environmental dependence for both spin and shape of galaxies. So I have Currently, I'm working on the real data using HSC new as 19A, so which is the new to measure the intrinsic alignment signal of luminous red galaxies, because luminous red galaxies have a relatively good photosay. So this is possible, and I hope such measurement can provide some information for the wavelengthing analysis done in the HIC field. I also show that in the direction that to apply intrinsic alignment as a cosmological probe, we developed a new shape estimator that can extract basically the dark matter halo surrounding the emission line galaxy, extract the shape information of the dark matter halo surrounding the emission line galaxies. And this provide a promising tool for the future surveys such as PFS and also DAISY. So the work in progress is trying to apply this estimator to the observed image instead of simulated one. So thank you for your attention, and I look forward to the questions.
Thank you very much for the very interesting talk. Are there any questions for Jingjing? And Mike?
Hi, Jingjing.
Hi.
Interesting. It went by kind of quickly. I'm wondering if you can go back to sort of in the first half of the talk, I guess. You had the intrinsic alignment split up into centrals and satellites.
Mm-hmm. Yeah.
Okay. So I'm just trying to parse this, see if you can tell me whether I have the right interpretation. So in this, the way this is expressed, it says in the bottom right-hand panel, that positive corresponds to a radial alignment. At least that's what I assume, right?
Yeah, at small scales, yes.
At small scales. But so what's happening, I guess that was the gist of my question. The picture that you have on the left makes sense on small scales, but I assume that on the largest scales, where it still looks positive, you're no longer, a one halo, pairs within a single host halo. You're talking about pairs that are in two separate halos. So the smallest K, and it still looks positive, which I assume still means they're radially aligned somehow. And I was trying to understand is that correct? Is that the right interpretation?
Well, you can see this is only true for redshift 0.5. So large scales, there is a signal, but small, high redshift, there is no clear signal. So I think this is kind of like, how can I say, the satellites at a higher redshift, they are not very well settled in the central, or the central is accurately new member. So the low redshift large scale satellite signal is mainly I didn't study in my work, but some people have shown that the satellites tends to distribute along the major axis of the BCGs. So they have their distribute has a preferential spatial occupation within the halo, and their orientation has a preferential like pointing to the central. So I should expect that this can cause also a large scale alignment signal as you described, yes.
So is that, when you say, so what is actually being measured? Is it the alignment of, I mean, you have satellites and centrals on the left, centrals on the left, satellites on the right, but the radial alignment I think of as, at least in your cartoon, it's more to do with the alignment of the satellite with the line connecting the central and the satellite.
Yeah, that's the radial alignment.
So then if you're talking about large scales where it's now two halo, where is the line? Is it between the central in the other halo and the satellite in a different halo, or I'm just trying to visualize what is actually being measured.
So I think it's mainly between satellites and the other, you can say central or dark matter halo, because those are the like large scale structure. For the satellites, for those satellites, it's hard to feel like the other satellites within the other dark matter halo, right? Because they are like the tidal field. It's mainly dominated by the big guys, so the massive ones. Okay. And the satellites are not very satellite fraction also decreases if we go to higher redshift, right? So I think that's the picture. So it's supposed to be satellite with centrals if we consider galaxies. Yes.
Right. Thanks.
Neil, did you raise your hand?
Yeah, sorry. Yeah, so hi, Jingjing. Very nice talk. So my question was, so at the end of your talk, so you mentioned, that the reduced inertia tensor gives a weaker correlation than the inertia tensor, and you mentioned that this is maybe because the outer parts of galaxies respond like more strongly to, to the tidal field.
Yeah.
So does that mean that in galaxies that the inner parts of the galaxies have shapes that are more round than the outer parts of the galaxies? Or does it mean that the principal axes in the galaxies twist as a function of radius?
Well, I think both of your points are right. So it is true that the inner, well, it depends on how you define the shape, right, in the inner region. So,
so if you draw, let's say, like contours of brightness or something like that.
Yeah, the center region is more round, and the outer region is more elliptical. And also, what you are saying is right. The major axis, like kind of like if you go to the outer region, it's more aligned with the tidal field. Yeah.
Oh, okay. All right. Cool. Interesting. Thanks.
Are there any other questions? Well, if not, we can again thanks virtually Jingjing, and see you all next week for the next seminar.
Thanks very much. That was a lovely talk.
Thank you. Thank you so much for having me.